Okay, hello physicists. Welcome to the first of our exam review sessions. Today we're going to go over basically the Unit 1 material. So my plan for the exam review is as follows. Your exam review is going to be counted as your last homework, and it's not going to be due until the day of the exam. So when you come to your exam, please bring it. I will be, I hope I will be posting this assignment later today. It's taken me quite a while to put it together just because I want the exam review to be as close to the exam as possible so that it's really worth your time to do it carefully, and then hopefully we can get good scores on our final exam that wouldn't require any retakes. So, all right. What did we do in the first unit? Now, my feeling is that the first unit of stuff was a little bit boring because it's all just setting up our notation. And then, you know, once you get your musical notation set up, then you can really start to play the songs. But, all right, so these are our big ideas: using consistent units, working with vectors, understanding the difference between average values and instantaneous values for things like displacement, velocity, and acceleration, understanding constant acceleration motion, understanding 2D projectile motion, and then understanding uniform circular motion. So already in our first unit we did quite a bit of stuff, and so it's going to be worth our time to go back and retread that today. Okay, so the first thing that we did that was sort of a little counterintuitive was having to change units from one type of unit to another. Now, let's say that in this particular case, we say we have feet cubed per minute, and we know that 1 minute is 60 seconds, and we know that 1 foot is 0.3048 meters. Now, the thing that I want to remind you of, and I know I showed you this example earlier this semester, but it doesn't hurt us to see it once more. If we want to change the minutes into seconds, that's not going to take us much effort, because I can go 1 minute is the same as 60 seconds, and then the minutes cancels out on top and bottom. What I want to remind you is that feet cubed is actually a way of writing feet times feet times feet. Okay, length times width times height. So that's your volume measure. And so if I wanted to get my feet times feet times feet to cancel, I need to use 3 copies of it in the denominator. So 0.3, whoops, 1 foot is 0.3048 meters. So that cancels out one of the feet, but if I want to cancel out all 3 of those, I need to cube this. So that's this thing times this thing times this thing gives me feet times feet times feet, cancels all those out, we get meters cubed on the top and seconds on the bottom. Okay, so I know that's a little tricky, but you know, in the examples that I'll have you do on your exam, it'll be something hopefully a little simpler like this, where again, I know I'm reusing examples, but it's been a while. So let's say that, and this, to be honest, is one of the problems that I saw on the most recent exam. I saw people, there's 1,000 grams in 1 kilogram. There were a lot of people who wanted to put 100 grams in 1 kilogram. Okay, so there's 1,000 grams in 1 kilogram. 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. And so 1 gram is going to be a lot of those. So just as a first look at a problem like this, you really want to make sure that you're going to give me a big number. So this is a very small number. That's not a possible one. I mentioned this because on the test there were a lot of people who gave me answers for two objects that were close to each other. I asked you what the gravitational force between them was, and I got huge numbers. And that can't be right. If you have two objects that are close to each other, and they're normal-sized objects, in our everyday life we don't experience very much gravity. So you do want to be a little careful about getting the right order of magnitude on these things. So in this one, if you start out with 1 gram and you want to go to units of atomic mass units, you'd have to go from grams to kilograms, 1,000 grams in 1 kilogram, and then you'd want to go from kilograms to AMUs, or just U in this case. 1.66 times 10 to the minus 27. And there my kilograms are going to cancel out, and I'm going to end up with U. So grams cancel, kilograms cancel. And then if I'm looking at this just from sort of a logical point of view, if I have 1,000 here, that's 10 to the third. 1,000 times 10 to the minus 27th is going to give me 10 to the third, 10 to the minus 27th. That would be 10 to the minus 24th. So it would be 1 over 1.66 times 10 to the minus 24 in the bottom becomes 10 to the 24 in the top. And then this is some number slightly less than 1. Okay, so it's probably around 0.6. So I would guess that I'm going to have something times 10 to the 23rd. Okay, another thing that physicists are very good at realizing that some people in other disciplines seem confused about sometimes, but if you add two things together, those two things have to have the same units. Otherwise, you're going to come up with nonsense. So here's a good example of that. Let's say you have an equation that has this form. V equals AT squared plus BT cubed. Okay, now time is going to be in seconds, and then velocity is going to be in meters per second. Okay, now let's look at this. V we already know, meters per second on one side of the equation. Now I have an equals right there, and if you have meters per second on one side of the equation, everything else on the other side of the equation must have those units. So this whole thing has to be in meters per second. This whole thing has to be in meters per second. But let's take a look. T squared is in seconds squared. T cubed is in seconds cubed. And so that tells me what kind of units I need on A and what kind of units I need on B. Okay, the kind of units I need on A, well, just to cancel out my seconds squared there, I need a seconds squared on the bottom. And then, to get it in meters per second, I'm going to have meters per second. So meters per second, and then having another seconds squared down there, times seconds squared on the top, will give me meters per second. So, in fact, seconds times seconds times seconds, this is seconds cubed. And then over here, same idea. Seconds cubed on the top means I have to have seconds cubed on the bottom, but then I need to take it times meters per second because overall I want to have units of meters per second. So this seconds times seconds cubed gives me seconds to the fourth. Okay, so the units on that are going to be meters per second cubed and meters per second to the fourth. Okay, now early on when we were trying to talk about vectors, the trick that we would always do is a vector is some sort of a pointer, and that pointer can be put into having x and y coordinates. And the trick then is that if you want to add two vectors together, for instance, you can add up the x parts and add up the y parts. Sorry. Yeah, so we all know that if you have a vector with some length r and you have an x and a y part, you could always write out the sine and the cosine of this angle in the standard terms, but in Unit 1, I showed you an even slicker trick for this, which is that if you define this as 0, 90 degrees, or pi over 2, and this would be 180 degrees, or pi radians. This would be 270 degrees, or 3 pi over 2. If you define it this way, and you draw your r anywhere in this two-dimensional plane, and there's your theta measured with respect to the 0, this is your x and this is your y, and then your x would be r cosine theta and your y would be r sine theta. Okay? And so then you're writing this vector here as the sum of its components. You have a rx and an ry. And of course, if you want to go backwards from that, you can. So for instance, if you have a vector that's written in component form, you can use your Pythagorean theorem and just have add up the magnitude of that vector would then be 2 squared plus 6 squared plus minus 3 squared, and then take the square root. The other thing to notice about vectors is that there's a very direct sort of visual meaning. So for instance, if I have this vector here, a vector A, if I had a minus A, it would just be pointing over here in the opposite direction. So that would be my minus A. And of course, the way that I would have that is just, if your A is, x, y, then your minus A would equal minus x minus y. And you can see how that gets translated through the origin. Okay, when you're adding up vectors, you just add up all of the components. So in this case, if I wanted to add up A and B, I would just have 6i plus 8j minus, so 1 plus a minus 3 is minus 2k. Let's see, is that the answer of any of these? It is. And you can do all sorts of other, more involved calculations with vectors. I know I put this question on your first test, and there were a fair number of people who got it wrong. So let's see how we would do this. If you have A, that would be 2 minus 3. And if you had minus 2b, I would take minus 2 times each one of these components, so that would be minus 2, and then this would be minus 2 times minus 2, so that would be plus 4. And now I could just add these together. A plus a minus 2b would be 0, and then I would add up these two and I would get a plus 1, so that would be if I wanted to write that in the ij way, it would be 0i plus 1j. Which is this one. Okay, I don't think I skipped. Okay, yeah. So beyond that, we had quite a bit of effort that we put into distinguishing between instantaneous and average. Instantaneous velocity, for instance, is how fast you're going right now. So that's what you would read off of your speedometer or something like that. On the other hand, your average velocity could be very different because it just requires you to look at the total displacement over the total time. In the instantaneous case, you let that time go to 0, but that is not necessary. On the other hand, there also is this idea of average speed where your displacements in that case are not taken into account. So for instance, if you go around a track like this and go and start and end at the same place, your total displacement is 0. So then your average velocity would be 0 because your total displacement over the total time would vanish. On the other hand, your instantaneous velocity would not be 0 because it would just be however fast you are going when you're going at that point. Your average speed would also not vanish because it would just be the total distance that you drove over the total time. Okay, and you can make the same sorts of distinctions with average acceleration and instantaneous acceleration, where average acceleration is the total change in velocity over the total time. Instantaneous would be how much your velocity is changing at a particular time. So, okay, so this is an example that I think I put on a review sheet a while ago, but it's useful. The idea is that you start at hither, you go to yon, and you go back. So you go, foop. Let me draw my arrow. Okay, so that's our story. It says the time for this trip is 2 hours. So your delta t is 2 hours. The magnitude of the average velocity of this car trip is, well, your V average is going to be total displacement over total time, but you ended in the same place where you started, so that's going to be 0 meters over 2 hours. So for this particular question, that would be your answer. On the other hand, I could ask you the speed average, which would be the total distance. In that case, it would be 100 kilometers in 2 hours, which is 50 kilometers. Okay, so those are different. Yeah. Let's look at another example. It says over a short interval near the time t equals 0, the coordinate of an automobile in meters is given by x equals 27t minus 4t cubed. Now, of course, as physics cognoscenti now, we know that if this is in seconds, this must be actually 27 meters per second squared. Meters per second. And then this is in seconds cubed. So this has to be meters over seconds cubed. Why? Because x is in meters. Okay, that's just a side note. It says, at the end of 1 second, the acceleration of the auto is. Okay, well, we know that the acceleration is simply found by taking the second derivative of the position. So the first derivative of the position tells us how is x changing. That's my velocity. So there's 27 minus 12t squared. And if we take the derivative once more, it would be a equals this derivative of a constant is 0. And the derivative of this would be minus 24t. And so at the end of 1 second, I would put a 1 second in there, and my acceleration would be minus 24 meters per second squared. Now notice, there is something interesting about this example, which is that almost every problem that we did in this course was a constant acceleration problem. When do you get constant acceleration? Well, you get constant acceleration when you have a constant force. Is that always the case? No, it's a special case. But it is a special case that's very useful for us to measure. And so we've done a lot of work, or I should say effort, since we're in physics class. We've put a lot of effort into understanding that particular case. Now let's take a look at another case. So that one was having us look at the instantaneous acceleration. What would we do if we wanted to find the average acceleration? Well, in this problem we have x equals 4t squared minus 3t cubed. X is in meters, t is in seconds. Okay. Its average acceleration over the interval from t equals 0 to t equals 2 seconds is. Well, if I want to find the average acceleration, then I'm not looking at the acceleration at any point in the interval. I'm just looking at what is my velocity at the end of the interval? What is my velocity at the beginning? How much did that change? How much time did it take? So my v, my instantaneous velocity can still be found by taking the derivative with respect to time of x. So this is going to be 8t minus 9t squared. And if I find my v at time equals 0, it would just be 0 meters per second. And if I had my v at time equals 2, it would be 16 minus 36 equals minus 20 meters per second. So if I wanted to find my average acceleration, it would be v2 minus v naught over t2 minus t naught. So this would be minus 20 meters per second minus 0 meters per second. And then on the bottom, it would be 2 seconds minus 0 seconds. And so that would give me minus 10 meters per second squared. Okay. Okay, now you can do the same sort of thing with displacements and velocities. So for instance, in this problem, it asks what's the average velocity if you go from x final, which is, you have an x initial rather that they give you. Let me call that an r initial. It's an initial position of minus 2.1, 3.7, and 1.4. And then you have an R final, which is 3.3, minus 1.1, and 4.2 meters. And the amount of time that you took is 5.3 seconds. And so if you wanted to find your average velocity, it would be R final minus R initial divided by the time. So I'm going to put this on your review sheet. I'll let you work out the numbers on that. Now for the last one in this section, is it the last? No, it's not. Just kidding. For a transitional one in this section, let's look at the graphical methods for solution. If you have a position versus time graph, how do you find the velocity? Well, remember, here's x, v equals dx dt. We're looking for velocity, so what is this in terms of the graph? This is the slope. So if you have a position versus time graph, we're looking for the slope. What is the instantaneous velocity at 7 seconds? That's right there. Well, the way we can find the find the velocity there is to look at the slope in this region. So let's see, my delta x over delta t, my rise over run, I'm going from 12 to 0, so I've gone down 12 meters, or rather backwards. And then from 5 seconds to 9 seconds is 4 seconds, so this should be minus 3 meters per second. And there we go. Okay, so let's do again. I just want to hammer home the difference between instantaneous and average. If you have the coordinates here, here's your x equals 16t minus 3t squared, or sorry, t cubed. Something to notice is that this actually is not the type, so I've already said this, but I'll say it again. This, if you have a t cubed in there, this cannot describe constant acceleration motion. It's where the acceleration is also changing. So that's called the jerk. The coordinate of a particle in meters is given by that. The particle is momentarily at rest at t equals what? Well, this might be a hard one to figure out, but what does momentarily at rest mean? Well, I am at rest when my velocity is 0. So what you need to do for this one is find v from x, 16 minus 9t squared. And then you can go ahead and set this equal to 0 and find out what time that happens at. So 0 equals 16 minus 9t squared. And then I can go ahead and find that t squared equals 16 over 9. T equals, I'm just taking the square root of this side. It would be 4 over 3 seconds, which is 1.33333, and here we are. Okay, so that's one type of problem. Let's see, can we look at another type of problem? Here we have each of 4 particles moves along an x-axis. Their coordinates are functions of time, and they're given like this. And it asks, for which of these particles is the velocity increasing as t is greater than 0? Well, for our last problem, we were looking at something about the velocity of the particle. Here we're actually going to be looking at something about the acceleration. Why? Because we're asking when is the velocity, we're looking for which the velocity is increasing. So velocity increasing, the idea there is that acceleration is going to be positive. So for each one of these, you could go ahead and solve for the acceleration. It's going to be the second derivative. So let's just look at particle 1. And I think you'll be able to see the pattern then. X equals 3.5 minus 2.7 t cubed. V equals, this is the derivative of that, would be 0. And then here I would get minus 3 times 2.7 times t squared. And then my acceleration would be minus 3 times 2, or maybe I'm doing my power rule for derivatives. 2 times 3 times 2.7 times t. Okay, so look at what this is. Because I had that minus out front at the beginning, I still have a minus out front, and this whole thing gives me a negative acceleration. So that one, the velocity is decreasing. Notice, however, that if I have a plus right there, this would give me a positive acceleration. So yes, plus right there, positive acceleration. Yes, minus, minus. No good. So that's the idea here, is that you're looking for which ones have a positive acceleration and eliminating those which don't. All right, and just a last one. You might remember this type of problem. It says, which of the five coordinate versus time graphs represents the motion of an object whose speed is increasing? Well, remember, velocity is represented by the slope of the x versus t. So as time goes on, which one of these has a slope that's getting steeper? Well, it looks like this one, because here the slope is not changing. Here the slope is getting flatter. Here the slope is also getting flatter, and here it's not changing. So in this one, you're going backwards and slowing down. Here you're going forwards and slowing down. Here you're going forwards and speeding up. Here you're going backwards at a steady rate. There you're going forwards at a steady rate. All right, now, then in this Unit 1, we spent a lot of time developing our constant acceleration model. And because we've just gotten out of our unit where we were doing problems with angular acceleration, these equations should not be so unfamiliar to you. The part that you might have not thought about for a while is how this is going to be used in for two-dimensional motion. So for instance, if I take a ball, if I take a ball and throw it across the room, shoot a projectile like this, I'm going to have to worry about how the ball is moving in the x direction and how it's moving in the y direction. And essentially the conclusion we came to back then, and we still agree with it, is that what happens is that the force of gravity is pulling down on the object. It's not pulling in the back and forth direction. And so my acceleration is only going to be in the y direction. In the x direction, I can treat that motion essentially independently, and my acceleration in the x direction would just be 0. And so I treat the x and the y motion as essentially independent, and in the x direction my motion is unaccelerated. In my y direction the motion is accelerated. So let's take a look at how we try to break up these types of problems. Here we're told a racing car traveling with a constant acceleration increases its speed from 10 meters per second to 30 meters per second. Okay, so let's write down what we know. 10 meters per second, what is that? That is the initial velocity. So v with a 0 on it. We end up at a speed of 30 meters per second, so that's our final v without a 0 on it. And this happens over a distance of 60 meters. Okay, so I could say, for instance, my x would be 60 meters for an x naught of 0 meters. And then the question it asks is, how long does this take? So I want to find t equals what? Now, the next thing that I do is, oh, wait, what don't I know? And in this case, you don't know a, the acceleration. And so when you're looking at your possibilities for this constant acceleration model, you have to go now and pick an equation that doesn't have an a in it. This is your only such equation, and now you're off to the races. Go ahead, stick in all the numbers, and solve for t. I'll let you do that. Now, one of the tricky things in this is that this accelerated motion can either be accelerating forward, getting faster, forward, getting slower, backwards, getting faster, backwards, getting slower. So for instance, if you had forward getting faster, your velocity would be positive and your acceleration would be positive because you're getting faster. If you were going forward but getting slower, then your acceleration would be positive, or sorry, your velocity would be positive, but your acceleration would be negative. It all just depends on the way that you define your terms. So in this problem, for instance, there's a north direction and a south direction. And, you know, I could define north as positive. And in this case, it says, a car moving with an initial velocity of 25 meters per second north. So in that case, I could say V naught equals 25 meters per second, and the north determines the sign. So forward is plus. But it has a constant acceleration of 3 meters per second squared south. So acceleration equals 3 meters per second squared south. So what's going to happen here is that my car is going to slow down, slow down, slow down, stop, go backward, go backward, go backward. And as it goes backward, then it would be speeding up. Going forward, slowing down, and going backward, speeding up, both have negative acceleration. Okay, then it says after 6 seconds, its velocity will be. So t is going to be 6 seconds, and you could just use your v equals at plus v naught. Okay, so this would be minus 3 times 6 plus 25. This would be minus 18 plus 25. So this would be give me a plus 7 meters per second. 7 meters per second is how fast my car would be going, and then the plus tells me that it is still going north. Okay? Now, here's the tougher part, is doing two-dimensional motion problems with the accelerated model. So that's what I was talking about earlier with the x direction being unaccelerated and the y direction being accelerated by the force of gravity, where near the Earth the force of gravity just looks like m times g, and then Newton's second law gives us F equals ma, and if the net force is the same as just the gravitational force, your mass times the acceleration is just going to be that mass times the gravitational field strength, and your acceleration in the y direction would just be your gravitational field strength, or 9.8 meters per second squared. So one example that we discussed quite a bit at that time was that of a airplane dropping cargo or dropping a bomb or something like that. If the airplane is going at a constant rate and drops a package, the package stays underneath the plane, and it's getting faster in the y direction as it goes down, but it's staying at the same speed in the x direction, you know, up to the level of a little bit of air resistance. So then it asks which one of these is not true. The bomber is over the target when the bomb strikes. That is true. The acceleration of the bomb is constant. That is also true. What is the acceleration of the bomb? It's g, the gravitational field strength, 9.8 meters per second squared downward. The horizontal velocity of the plane equals the vertical velocity of the bomb when it hits the target. That cannot be true. Why can that not be true? Well, the reason it can't be true is that in this case, the bomb is already going the same speed as the plane when it's dropped. So as it accelerates, it has to be getting faster and faster and faster. So it must be going faster than the plane, because the total speed is going to be the vector combination of these. So I'd have to use my Pythagorean theorem and combine my x squared plus the y squared, and then take the square root. Bomb travels in a curved path. Yes, the time of the flight of the bomb is independent of the horizontal speed of the plane. Also true. Why? It's because it only depends on the height with which this bomb is dropped. So here's a question I gave you on test 1, and I think I'm going to give it to you again because there was a lot of confusion over this one. And I think when I gave it to you back then, I split it up into a short answer. That seems like a good strategy again. It says the airplane is in level flight at an altitude of 0.50 kilometers at a speed of 150 kilometers per hour. Okay, so your y naught is 0.5 kilometers. Your v naught in the x direction is 150 kilometers per hour. And it asks, at what distance should it release a heavy bomb to hit the target at x? Okay, so you want to find x, essentially. And so let's see what we have to work with. Well, in our x direction, our position is going to be just dependent on the initial speed times t plus x naught. So let's set that x naught to 0. And this x is going to be that distance d, that this is what we want to find. And we are given this in 150 kilometers per hour. You need to convert that, however, into meters per second so that it plays nicely with your g. However, at this point, I don't know what t is. So now let me write down, what do I know in my y direction? In my y direction, I have y equals 1/2 at squared plus v naught in the y direction times t plus y naught. Well, my y naught now is going to be 0.5 kilometers. My y at the end of the story is going to be 0 kilometers. And I want you to remember that you're going to have to change the units here so that this is in meters. So this would be 500 meters. Your initial velocity in the y direction is 0. Why? Because I'm not lobbing this up. If I'm just lobbing it forward, it starts not moving up and down, and it only starts moving in the downward y direction because of the gravitational acceleration. So this term goes away. Here your acceleration in the y direction is minus g. Why minus? Because it's downward. So what is your strategy here in this problem? You're going to go ahead, solve for t, put that t in here, and then solve for x. Okay, so there's kind of a lot of steps in that problem. I think if I give it to you on a test, I'm going to break it down a little bit more than that. And as I said, when I give you this review sheet, which I hope to finish this afternoon, it will break all this down. All right, so that's as far as I want to go today. So what's coming? Well, this week on Friday, I want you to retake your first concept inventory test that we took at the very beginning of this semester. And I don't want you to study the FCI itself, but I will say if you can score better than you did on your original, I will give you those points as quiz extra credit points. So might be worth taking seriously at least. Okay, so on Friday we're going to do a little bit of, we're going to go over rotational motion and try to connect that to gravity, and then we're going to take the FCI for the second half of the class period. Monday and Wednesday of next week are going to be more review. Friday of next week, I believe you have off, and then our exam is going to be not this coming Tuesday, but the Tuesday after that, May 4th. And my idea is that at the time of the exam, you will give me your review packet. Okay? And remember, I am giving you 5% extra credit on the exam for doing your course evaluations. So please do them. And then hopefully we will all have an extra, a final exam score that doesn't need any retakes. All right, so thank you for watching, and make sure that you email me if you have any questions.